And I have a graph already inputted in here. This is more of a physics-related experiment, but for the purposes of just knowing how to take this data, which you already know how to enter, and seeing a line like this and being able to write an equation from it. So I do want to point out, notice that, although I think this is a little bit cut off here, at the bottom there's a label and unit for time. Our y variable, position with units, notice, important, and we have a title on our graph. So we're going to utilize a method called linearizing, and so we're always going to evaluate the line on the graph to know how straight it is. And an easy way to evaluate right after you put in your average data is to use the linear fit key. And so I'm scrolled up here to this R equals, and there's a red line on that button. I'm going to click that, and that's called linear fit. And what the computer has done is it has drawn the best fit line, and it's this black line that runs through all of the data points equally. Now I think in math class you call this the line of regression. So same thing, this is the line of regression through that data. And a box even pops up with some important information that we're going to use. Now the piece of information that we want to analyze to know if we do have a linear fit graph is this correlation right here. And notice that it says 0.9998. And if this was perfectly correlated to this straight line, that number would be 1. So this is very close to 1. Notice my red data line is not deviating one way or another, so I think it's pretty safe to say that this is a linear relationship. So because of that, we're going to utilize this y equals mx plus b form, which is our general equation for any straight line, to write a specific equation for this particular data set. So to do that, I'm going to get a text box and place it down here by going to Insert, and I'm going to choose Text, and it shows up here. I kind of like it down here just so it's a little bit more organized, so an easy way to do that is to choose Page and Auto Arrange, and so here it is. And I might make it a little bit bigger just so you can see it better. Not necessary maybe when you're working. I might have to move that around a little bit as we're talking here. So in this text box, I'm going to write my mathematical model that would fit this, again, linear relationship. I'm always going to go back to this y equals mx plus b. Now this is a very general equation, but what we want to do is make it very specific for the relationship, and that's what's going to make it meaningful. So to start off, instead of y, I'm going to put something in there that would represent what is on the y-axis. So notice on the y-axis is position. The units are meters. So maybe I'm going to choose a symbol of a p to use for position. So I'm going to put p equals. Again, instead of generic y equals, I'm saying p equals. Then notice in this general equation I have an m. M is our symbol for slope. Now the computer tells you what this slope is, but I need you also to remember from your math knowledge where slope comes from, and it comes from the change in y for every 1 unit x. And so the computer has taken 2 points along this graph, found the change in the y of those points, divided it by the change in the x of those points, and averaged it to this number right here. So instead of just the m in the equation, I'm going to put what that number is, and that number I'm told is 0.2574. The other thing is, because this is a measurement, just like any measurement, it's very important to have units behind it. And the units, because this number comes from y divided by x, and our y unit is m, and our x unit is s, even though I think it's cut off down here, then that number would be m divided by s. So notice I put that in parentheses just to make it a little bit neater. Okay, next in our general equation is an x. And again, instead of a generic x, I want to put something that's meaningful for what the x variable is in this graph. And so notice that in my x column over here, it's time. So I'm going to put a t then to represent time. All right, then we have a plus sign in our equation, and then we have a b. And if you forget what b represents, it even tells you here in this linear fit box, it represents the y-intercept. The y-intercept is always the point where x is 0 and the line crosses the y-axis. So it's the y value when x is 0. Again, the y-intercept is the y value when x is 0. So notice this red data line did not extend to the y-axis, but our line of regression or our linear fit analysis has extended it back as if where it would approximately cross the y-axis. So when time, which is on our x, is 0, this is the point right here that our data, if it extended back, would cross the y-axis. And so the computer has given us a measurement of that just above 0 here, 0.01608 meters. Now, before I can just stick that number into B, we are going to do a little analysis about this. Because of the fact that this is an extended line, it's really, it's not actual data, we want to evaluate if this number is meaningful or not. We want to know if it's significant, or is it within the error that we know lies in this data line that we are going to ignore it. And so to do that, we always run what we are going to call the 5% rule. So in the text box over here, I'm going to give you generally what the 5% rule is, and then I'm going to show you how we're going to calculate it for this particular example here. To calculate we need to calculate a percent, and what I'm going to do is take the y-intercept and divide it by the highest y value. And I guess I'm going to put this all in parentheses, because then the last thing you need to do is multiply it by 100 to make it a percent. I'll put that. So y-intercept divided by highest y value times 100%. Now, if you have not been writing this down, this is a really good thing to jot down, especially on maybe one of your reference sheets, so that you always have this in front of you, how to calculate it. I'm not interested that you memorize this equation or this relationship. I want you to know how to do that. So this is, again, a good thing to jot down on those references that you can use. Now, the other thing you might want to jot down is how to evaluate this. If this number comes out to be less than 5%, we're going to say, well, the y-intercept is close enough that this number that was given is not significant and it's really equal to 0. So what this means is the given, whoops, not significant. If it is greater than 5%, however, we're going to put in the given value. It is significant to the relationship. Now I'm going to tell you, sometimes it is significant to the relationship. Sometimes, though, it's not. It doesn't make sense at all to have a y-intercept of some number here. And what that means is that you probably had more error than what we're allowing. We're allowing ourselves 5% error with this rule. And so those are all things that you're going to be discussing in your lab report. So I'm going to run the 5% rule with this particular example. So my y-intercept is 0.01608, and I need to divide that by my highest y value. So I can go here to the data table and I can see that in my y column, my highest y value is 2.586. And again, once I get that number, to turn it into a percent, to evaluate it, I'm going to take it times 100. So let me grab my calculator. Even though maybe you've realized we probably don't need a calculator on this one, because this is a very small y-intercept number that we're given anyway. But just for fun, I'm going to calculate that, and that percent comes out to be 0.6218. And I can have 4 digits there because these two measurements This measurement has 4, and this one also has 4. So I can keep 4 digits in my percent here. Notice it's not even 1%. So maybe you want to punch that into your calculator, check to see if you get the same number as I did. Very low percent. Clearly it's less than 5%. So that means this given number that has been estimated from the linear fit line or the line of regression is not significant to this particular relationship. So when I go here to my equation, I'm going to put in 0 for the b-value. And I'm going to put units behind that too, because it is a measurement, it's a value, and the units on the y are meters. So that means this value that comes from the y would also be meters. So what I have here now is a mathematical model from this data set. In front of you originally we had just the graphical model, but with a little bit of analyzing we have also turned that into a mathematical model. Mathematical models are very important to us because they allow us to predict circumstances that were not tested. So for example, this is a test about a buggy in position and time. The last time that a position was recorded was at 10 seconds. But I know the mathematical model now of this buggy, and I could predict where this buggy would be at 20 seconds. I would put in 20 here for time and calculate out the change that would occur for every second, or 100 seconds, or 1,000,000 seconds. I know the relationship, so we can use this to predict. Or maybe I want to know at what time the buggy would be at a certain position. I could put in a position here. I could put in 1,000,000 meters, and I could calculate the time reading that it would be to go 1,000,000 meters. Later, we're also going to talk about the specific meanings of slope and y-intercept, and the things that you should include in your lab report for that as well. But for now, you should be ready to do some practice graphs and practice mathematical models. So check out that assignment and graph it up.